Testing. Okay, welcome. This is our second session on algebra and number theory. And today we're going to look at rings and several examples of rings and a concept called units. Okay, so a ring R plus multiplication is a set R with two binary operations, addition and multiplication, or they could be some other abstract binary operations, but usually these are the most relevant. So just use these symbols to talk about them, such that R together with addition is an abelian group with identity 0. Okay, but again, that could be another abstract letter other than 0, but all of the rings that we will be interested in here will be rings that contain 0. So R plus is an abelian group. Now, last time we studied abelian groups and considered many examples of those. So this extends that concept a little bit. Okay, so the next axiom, R together with multiplication, satisfies that multiplication is associative, that there is an identity element, 1, or some other letter, but 1 will be relevant here. So there's an identity element 1 that's neutral in the sense that A times 1 is equal to A, which is equal to 1 times A for all A belonging to the ring R. Okay, next, multiplication distributes over addition. So an example of this is for all A, B, and C belonging to the ring, A times B plus C is equal to A times B plus A times C. And the other way around, as in if you had this on the other side, we would have the same thing. As in B plus C on the left times A on the right equal to B times A plus C times A. Now notice that I don't put those in alphabetical order because we don't necessarily know that this multiplication is commutative. Okay, and notice also we haven't mentioned inverses for this operation either. They don't necessarily exist for multiplication in a ring. Okay, so we're going to look at 5 examples here. So the first one is just the set of integers. The second one is integers modulo 6. The third one is integers adjoin 1 plus root 5 over 2, which we'll talk about more in a moment. And the fourth one I've got here on the list, which is just under the page here. I can see it, you can't, but that's okay. I want to keep this paper where it is. The ring of 2 by 2 matrices with integer entries. And then the last ring I want to talk about today is polynomial rings. So the set of all polynomials with, let's just say integer coefficients, because that's an example of one. Okay, so let's get started here. So we've defined a ring. I want to keep that definition there for a while. So let's start looking at our examples. So the first example says that integers together with addition and multiplication is a ring. Okay, so let's consider this. So we have integers together with addition is an abelian group. And in case you forgot what that means, it means that this structure is a group and the addition there is commutative. In other words, A plus B is equal to B plus A. Okay, so the identity of this group is 0. So 0 is identity because 0 plus A is equal to A, which is A plus 0. Okay, and every element has an inverse, so the inverse of A is just minus A because they add together to give the identity 0, and that's the same the other way around. And we know this because we have commutativity. Okay, so this here shows us that we have an abelian group. So the next, it shows us that we have a group. So the next thing is to note that it's commutative. So for all A and B belonging to the set of integers, A plus B is equal to B plus A. Okay, so here's our first example done. This is a ring. But I also wanted to talk to you about units of rings. Okay, so this is an example to consider the units. So units, or a unit, just put epsilon of a ring. R is an element of that ring satisfying that there exists a multiplicative inverse. Exists such that epsilon times epsilon inverse is equal to 1. Now, not every element has a multiplicative inverse, only some of them do. Because if you think about the integers, just take the number 7 for example. Does there exist a number a, an integer a, such that this is equal to 1? Well, not in integers, right? So if that's the case, then we would have a is 1/7, but 1/7 is not an element of the integers. So a is not invertible. Okay, so this is an important concept because we're going to study fields after this. And if you understand the units, then you'll have a better understanding of fields. Okay, so given this definition of a unit, then the question is, well, what are the units of this ring? Which elements do have an inverse? Okay, so with that in mind, if A times B is equal to 1, then if we now solve for B in terms of A, B is equal to 1 over A. Now we can see that we require A to be non-zero, okay, in order for such an inverse to exist, because otherwise this is even undefined in the real numbers. But we also need this fraction 1 over A to be an integer. So 1 over A belongs to the set of integers if and only if, and I'll write IFF for if and only if, A is equal to plus or minus 1. Okay, so this means that the only units of the set of integers are plus or minus 1. So I'll just put U, maybe I'll just make this curly for the set of all A belonging to Z such that exists B satisfying A, B equals 1. And we've decided that this set is just the set containing plus or minus 1. Okay, so that completes our discussion of the first example there. So let's move on to talk about our second example, which is integers modulo 6 with addition and multiplication. So we claim that this is a ring. Okay, so let's just, because we're already familiar from our last session about what the elements of integers mod 6 is, it's the remainders upon division by 6, and there are only 6 of these, 0, 1, 2, 3, 4, 5, when you take the least non-negative integer that is a remainder modulo 6 when dividing by 6. Okay, so we want to take representatives. Now we've already studied similar things in terms of groups in the last session. Okay, and in that session we talked about Cayley tables. So let's just write the Cayley table for both addition and multiplication, and then let's decide whether we in fact have a ring in this structure. So first we'll put addition, and then I have 0, 1, 2, 3, 4, 5. That's 6 numbers there. I'll put those down the column 2. And then I'll gently draw some row separators. And column separators here as well. Okay, so that's for addition. Now let's do the same thing for multiplication. And I would hope that you will write some notes down yourself, because I feel like you'll have a better chance of taking this in if you do. Okay, so let's do addition first. Now 0 plus 0 is 0. 0 plus 1 is 1. Okay, we know we have the same thing here because 0 is neutral. And the same thing down the column because this is abelian. Okay, 1 plus 1 is 2. 1 plus 2 is 3. 1 plus 3 is 4. 1 plus 4 is 5. 1 plus 5 is 6. But when we reduce modulo 6, we get 0. Is that right? 1 plus 5, 6 gives 0, yeah. Okay, so next, my phone's ringing. Better turn the volume off. Okay, so we can do the same thing down this first column. And now 2 plus 2 is 4, 2 plus 3 is 5, 2 plus 4 is 0, 2 plus 5 is 1. And likewise, down here, 3 plus 3 is 0, 3 plus 4 is 1, 3 plus 5 is 8, which reduces to 2 modulo 6. 4 and 4 is 8, which we worked out as 2. 4 and 5 is 9, which is 3 mod 6. 5 and 5 is 10, which is 4 mod 6. Okay, so we filled out the Cayley table there for addition. Now let's do the same thing for multiplication. So 0 times anything is 0, so I can just put 0 in this row. Same thing down here. And incidentally, this structure is going to be commutative here because multiplication in integers is commutative, so it would follow that multiplication of remainders is commutative also. Okay, now 1 times all of these numbers is 1, 2, 3, 4, 5. And the same thing down the column. Okay, 2 times 2 is 4, 2 times 3 is 6, but that's 0. 2 times 4 is 8, that's 2, and 2 times 5 is 10, which reduces to 4. Okay, 3 times 3 is 9, which reduces to 3. 3 times 4 is 12, but that's divisible by 6, so we get 0. 3 times 5 is 15, which is 3 more than a multiple of 6. Okay, 4 times 4 is 16, but that is 4 more than 12. And 4 times 5 is 20, which is 2 more than 18. 5 times 5 is 25, which is 1 more than 24, and of course 24 is a multiple of 6. Okay, so now we've got the Cayley tables for each of these structures there. And we can see from this one that we have an abelian group here. We've got the identity in every row and every column. We have associativity, and every element has an inverse. So, sorry, the identity does what it's supposed to. The 0 being in every row and every column tells you that every element has an inverse. Okay, now the identity of this structure here is 1. So 1 is the identity of this one. 0 is the identity of this one. So the question is, do we have 1 in every row and in every column there? And the answer is no, we don't. We only have a 1 here and a 1 here. Okay, so we see then that not every element has an inverse. However, we do have multiplication satisfying some nice properties. So multiplication is associative, and I'll just abbreviate that because we've got it right there. 1 is the identity, so is neutral. And multiplication distributes, I'll just put dist, over addition. Because we inherit this from the integers, right? It works for integers, so it works when we reduce modulo 6. Okay, so we have all of the properties that we need for this to be a ring. Okay, so our next question is, okay, so we have a ring. Now what are the units, right? So remember what a unit is. It's an invertible element. Okay, so if we don't have 1 in every row and in every column, where do we have the 1s? We have the 1 corresponding to this one and this one. So let's write units. And this is a separate question, right? We've shown that it's a ring. So now we're interested in units. So 1 times 1 is equal to 1. And 5 times 5 is equal to 1. So the units are just 1 and 5. Okay, which brings me to another concept which we'll do in another session, but the concept of greatest common divisors. So I'll say an element A of integers mod m with multiplication. Okay, so I mean just the structure with multiplication. So is invertible if and only if GCD of A and M, meaning the greatest common divisor of A and M, is equal to 1. Okay, so this is a well-known fact about systems of remainders modulo M. Okay, so let's have a look in our Cayley table. Now, what is the GCD of, so in this case, we're interested in A such that GCD of A and 6 is equal to 1. Okay, so which numbers are relatively prime? So relatively prime is a phrase for when you have a GCD of two numbers equal to 1. So which numbers are relatively prime to 6? Okay, so the number 1 has a GCD of 1 with 6 equals 1. 2, the GCD of 2 and 6 is 2, because 2 is the greatest divisor of both 2 and 6. The GCD of 3 and 6 is 3. The GCD of 4 and 6 is 2. And the GCD of 5 and 6 is 1. Okay, so only 1 and 5 satisfy this. Okay, as we expect, because we've already worked out that those are our units just by looking at which rows the 1 is in, which row and column the 1 is in the Cayley table there. Okay, great. So moving on to our next example. Which is the set of integers adjoin 1 plus root 5 all over 2 together with addition and multiplication. Okay, now first I need to define what this symbol means, okay? So if I let's let 1 plus root 5 on 2, let's let this be omega. Okay, so then this with a square bracket around the omega, integers next to it. So this is a ring, okay, and this is a number. Let's just call it a number for now. But what this means is this is basically the set of all A0 plus A1 omega to the power of 1 plus A2 omega squared plus dot 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 plus an omega to the power of n, such that all of the a subscript j belong to this set, which is integers in this case, and n is a positive integer. So put a superscript of plus there to mean positive integer, but now that I think about it, I've used a times for something else, so I'm going to change this to say in brackets greater than 0, okay, because I don't want to confuse the notation there. Okay, and we've missed one more thing. An is not equal to 0, so we want our leading coefficient to be non-zero so that we can say that this has degree n. Okay, so this is exactly this, and it has a relationship with polynomial rings, which we'll study later. Okay, now, but if you notice there's something nice about this number, that's a square root, right? So let's just work out, okay, what is omega squared? So omega squared is equal to, so we have 1/4, and then we have 1 plus 2 root 5 plus 5. Okay, so if we simplify this, we have 1 over 4, and we have 6 plus 2 root 5. Okay, and now there's a 2 in both of those, so we can cancel a 2 and say that this is 1/2 3 plus 2 root 5. Okay, now that 3 is 2 plus 1. And then we can bring that 2 out and say that this is 1 plus 1/2 of 1 plus, oh, I should have gotten rid of that, 1 plus root 5, which is in fact 1 plus omega. Okay, so we've deduced that omega squared is 1 plus omega. So what that means then is that you can replace this omega squared there with 1 plus omega, and then when you expand that a2 and distribute across the 1 plus omega, you will have in terms of no omegas and omegas, so you can basically represent this third term there in terms of new coefficients, say a and b, to go there, right? Now you can also do this with the cube, because omega cubed has to be equal to omega times 1 plus omega, which is omega plus omega squared, which is omega plus, according to this, 1 plus omega, which is 1 plus 2 omega. Okay, so we can do the same thing with the omega cubed term that would appear here where my pen is. Okay, so in fact we've learned then that integers adjoin omega, where omega is 1 plus root 5 on 2, is actually equal to the set of a plus b times omega, such that a and b belong to the set of integers. Okay, so this looks much simpler than what we have up here. Okay, so given that, now the claim is that, how do we show that this thing is a ring? Okay, so what we want to do next is, well, we would say that associativity, we have associativity. Okay, so associativity. Yes, is inherited from the associativity of the real numbers, right? We know that the real numbers have an associative structure, and these are in fact real numbers, so this is a subset of the real numbers. And it's a proper subset. So I don't put a line under that. Okay, so we have associativity. So now let's move on and discuss the other axioms that we need. And I didn't actually say I'm talking about both plus and multiplication for associativity there, right? Okay, so actually on this little page here, why don't we finish off the fact that this together with addition is an abelian group. So we have associativity, the additive inverse, so a plus b omega plus minus a minus b omega gives us a minus a plus, in brackets, b minus b times omega, which is 0. Okay, so this is the additive inverse of this one, and this is the identity. Okay, so we can see that we have an abelian group in the additive structure there. And we've already considered the associativity of the multiplicative structure. So what remains there is to just say that multiplication distributes over addition and say what the identity is for multiplication. All right. So multiplication distributes over addition since inherited from the same property in the real numbers, right? So in other words, A outside of B plus C. Actually, I should put alpha, right? Alpha, beta, and gamma, because these are elements of this ring here, and we've already used A and B for integers. So this is equal to alpha times beta plus alpha times gamma, and on the other side, beta plus gamma here times alpha on this side is equal to beta alpha plus gamma alpha. Okay, now we also happen to have in this ring, we happen to have commutativity, but that's not something we need to verify in order to say that we have a ring. Okay, so these are actually the same number in this case. All right, and then 1 is the identity of this ring. All right, so now that we have that, let's just consider what multiplication looks like. Okay, so we have A plus B omega times C plus D omega. Now if we expand this out, we get AC plus AD omega plus C, well, let's just write BC plus BC omega for these two, and then plus BD omega squared. Okay, but we have a nice identity for omega squared, so we can simplify this a fair bit, right? So we have AC so far, then we have AD plus BC outside of omega, and then we have plus BD omega squared. But this is because we know that omega squared is 1 plus omega, so we can expand this and simplify, and we have then expanding this over that addition, we have AC plus BD, and then we have plus AD plus BC plus BD times omega. Okay, so this is what our products look like in this particular ring. Okay, so now that we have that, and we know we have a ring, let's consider what are the units. Okay, so suppose now that alpha times beta is equal to 1. And I'll say that we're thinking about the units here. Okay, suppose alpha times beta is equal to 1. Okay, so you can think of this as alpha, this is beta. So let alpha equal A plus B omega, and beta equal C plus D omega. Okay, now if their product is equal to 1, then what we have is simultaneous equations. So we have AC plus BD is equal to 1, and we have AD plus BC plus B plus BD is equal to 0. Hope that's visible enough there. Okay, so solving this, solving for C and for D, we will get that C is equal to A plus B all over A squared plus AB minus B squared. And D is equal to minus B over A squared plus AB minus B squared. Okay, now we need C and D to be integers. So that means then that that this divides into B and this divides into A plus B, right? But what this is going to mean is that we're actually searching for these two denominators, which are the same denominator, incidentally. We need that to be equal to 1. Okay, we require that A squared plus AB minus B squared is equal to 1. Okay, and now what we want to do is, in order to seek solutions to this, is called a Diophantine equation, we might want to complete the square here. So let's say completing the square. And now what we'll do is we'll multiply throughout by 4. So 4a squared plus 4ab minus 4b squared is equal to 4. And now this part of it here is almost a square. I'm just missing a b squared in there. Okay, so I want to write this as 2a all squared plus 2 times 2a times b, and then I introduce a b squared and subtract it away over here. I still have the minus 4b squared, and this is still equal to 4. All right, and so now this here is a perfect square. So we have 2a plus b all squared, and this here is minus 5. B squared is equal to 4. And so this 5 reappears. Remember, we had a square root 5 earlier. And so essentially, if I now relabel this one x, I'm looking for x squared minus 5y squared is equal to 4. Okay, and now I want the solution with the least x and y, least positive x and y that I can possibly find. So I could search through. Now a simple way to do this is ask yourself when is the square root of 5y squared plus 4, when is this an integer? Right? And you could run through with a computer calculation y values until you got an integer, and then you find a solution. But this can be slow, right? There are more sophisticated methods but continued fractions faster, right? But it takes a while to set up the continued fraction approach. Okay, so this we want to solve this. Now, simple, actually plus or minus 4. This should have been plus or minus 4 throughout. Plus or minus 4. And up here as well, plus or minus 4. And plus or minus 1 is what we need for that to give us integers in it for C and D. Okay, so now that we know what we're looking for, x equals 1 and y equals 1, give us minus 4. And it's actually the least solution we can find. Okay, so translating that back to this term, right? So we've got basically the y is the b. Okay, so b is equal to 1. So 2a plus 1 is equal to 1. So that says that a is equal to 0. So a equals 0 and b is equal to 1. Give us what we're looking for here. Okay, now if we translate this one back to our c and d, and this incidentally corresponds to 0 plus 1 omega, which is omega. Okay, so what we're looking for here, so we've worked out that omega has got to be a unit. Now the question is, what is its inverse? So remember we had a formula for C and D, which we write here on the left page. Okay, so in this case we got this denominator being minus 1. We found out that the A is 0 and the B is 1. So C is equal to 0 plus 1 over minus 1. And D is equal to minus 1 over minus 1, which is equal to plus 1. And this C is equal to minus 1. Okay, so that tells us then C plus D omega is equal to minus 1 plus 1 omega. Okay, so that says then that the inverse of omega is minus 1 plus omega, and this gives us 1. Okay, I'll put a little box around this. And in particular, this omega is our generator, because from this omega we can get all units. So all units, all invertible elements of integers adjoin omega are of the form omega to the power of m, where m is an integer. Okay, and I haven't specified that it's positive or non-zero there. Okay, great. So that completes our discussion of integers adjoin that particular omega. So the next example I'll discuss with you here is the ring of 2 by 2 matrices with integer entries. Okay, so we'll say this is a calligraphic R with addition and multiplication, where in this case R is equal to the set of all 2 by 2 matrices A, B, C, D, such that A, B, C, and D are integers. Okay, so now this is not quite all of the 2 by 2 matrices, right? But we know some properties of 2 by 2 matrices, that we have additive inverses, right? So we have R together with addition is an abelian group. Okay, and because we have, say, A1, B1, C1, D1, plus, let's see, our neutral element E is 0, 0, 0, 0. And actually, I didn't need the subscripts here. But anyway. Okay, and this is the same the other way around. Okay, so we have an identity. So E is equal to 0, 0, 0, 0. Every element has an inverse. So A, B, C, D plus minus A, minus B, minus C, minus D is equal to 0, 0, 0, 0. And the other way around, because this is commutative. So we see then that we have R together with addition is an abelian group. Okay, now next we want to consider multiplication. Okay, so multiplication is associative, and we inherit this. So it's inherited from associativity of the ring of 2 by 2 matrices. So just say 2 by 2 real entry matrices. Okay, now the neutral element here, so the identity, so E of multiplication is just 1, 0, 0, 1. Okay, because if I multiply a 2 by 2 matrix times this, I just get the same 2 by 2 matrix A, B, C, D. And conversely, on the other side, this identity matrix, and we have a symbol for this, right, uppercase I, identity times A, B, C, D gives us A, B, C, D as well. Okay, so we have a neutral element of this that works for all elements of the ring. Now, multiplication distributes over addition is our next property. Right, and again it does so since it does for these 2 by 2 real entry matrices. Okay, so we see that we have a ring. So now that we have a ring, let's consider the units of this ring. So which elements of this ring are invertible? Okay, so if you think about this, we're seeking all of the 2 by 2 matrices that have an inverse, right? But if you remember what the inverse of a 2 by 2 matrix is, right, you would take the determinant, divide by that, which is AD minus BC, and then multiply that by the matrix obtained from swapping the A and the D and putting a minus sign in front of the B and the C. Okay, but now the question is, when does this have entries in integers? Right, and also you need this here to be non-zero, right? And AD minus BC not equal to 0. Okay, so in general, what you need then is, so in general, we need AD minus BC to be equal to plus or minus 1. Okay, now there's a special name for the set of all matrices that satisfy this. It's called GL subscript to Z, right? Or general linear group And this is the set of all A, B, C, D such that A, B, C, and D are integers satisfying AD minus BC is equal to plus or minus 1. Okay, and oftentimes when you have a ring, you can associate it with a subring of a 2x2 ring of matrices. Often you can, right? And that would be called a representation. Okay, so this one is a very important multiplicative group in algebra and number theory, and even in other branches of mathematics. Okay, so this group of units it's a subgroup, or sorry, it's an additive subgroup, but it's a set of all multiplicative elements in that ring, and it's also therefore a subset of that ring. Okay, so we'll just say GL2Z is a proper subset of this ring, which was 2x2 matrices with integer entries. Okay, so I think that completes our discussion of that matrix ring there. So we'll move on to my last example of a ring here and the units of that ring, which is, and we've already seen this notation here with the square bracket and then something next to it, but this time, this here, I want to treat this as the variable x. Okay, so this is a ring. Now what is it? Well, remember what we did in terms of z adjoin omega. So let's see if I find the page for that. Okay, so if I bring this back up, right, so z adjoin omega with a square bracket there means all possible sums of these, where omega is that number, right? But instead, if omega is x, the variable x, then we don't have this nice property that omega squared is 1 plus omega, so we can't simplify that tremendously, right? Okay, so what this is here is this is the ring of polynomials. So ring of polynomials f of x with coefficients in the set of integers. Okay, so let's just describe with some symbols what this is. It's the set of all a0 plus a1 x to the power of 1 plus a2 x squared plus dot 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 plus a n x to the n, such that all of the a subscript j belong to this set there, which is integers, and n is a particular positive integer. Or actually, it could be just non-negative, all right? So put greater or equal to 0 there in brackets, because n could be 0. It needs to be finite for it to be a polynomial. And actually, we've missed one more thing. Given that we had to say this there, we need a subscript n to be non-zero. Okay, so this is the definition of this polynomial ring here. Now it is a ring because this, together with addition, is clearly an abelian group. Right, so we add any two polynomials, say f of x. All right, so if f of x and g of x are two polynomials with integer coefficients, then f of x plus g of x is also an integer polynomial. So it's closed under addition. They don't necessarily have the same degree, but it's closed under addition. We have 0 is our neutral element, so 0 plus f of x is equal to f of x, which is f of x plus 0. So 0 is the additive identity. Okay, now let's look at the inverse, additive inverse, that is. So f of x plus minus f of x, right, would be just f minus f, which is the 0 polynomial. So every polynomial f has an additive inverse minus f of x. So we see we have an abelian group here, and we get associativity from the associativity of the integers, right? Associativity is often the most difficult part of proving something is a group or a ring, right? So associative, I'll just give you a sort of a sketched proof of that here. So let f1 of x, f2 of x, and f3 of x belong to this set. Then we have, and assuming that we can write these as a sum, right? So f1 of x plus, in brackets, f2 of x plus f3 of x is equal to, now we just replace these by their sum. So the sum of the a j's, so as j goes from 1 to, say, n subscript 1, x to the power of j, so this is our f1. And actually I'm going to need a superscript here, and when I do that, when I don't mean a power, I'll have to put a bracket around it, okay, to refer to the one that's there. All right, and so we add in brackets a similar thing here for the f2 and the f3. So we have a j superscript 2 with a bracket around it, x to the power of j, a j superscript 3, x to the power of j, and it goes from j equals, actually j goes from 0 up to n2, and this one up to n3. All right, so what we do next, now we know each of these parts of the sum, so each of the summons in here can be looked at individually, and we have associativity on each of those, right? So that means that we can look at each of the summons, and we have associativity on the summons, so we can move that bracket around, right? Now there are a lot of things to write here, and it's fairly tedious, but it means you can move the brackets. So I'll just say can move brackets. Okay, so it's associative. Okay, so now that we have that, let's consider multiplication. So we know multiplication is going to be associative. Well, actually, I mean, that's a bit involved to do, right? So just say ... involved. Okay, I'll just tell you it is. Now, what is the identity of multiplication in this ring? It's just 1, because 1 times f of x is f of x, which is f of x times 1. Okay, so we have an identity element. Multiplication distributes over addition. So f of x times g of x plus h of x is equal to f of x times g of x plus f of x times h of x. Right, and this would be a little bit involved to demonstrate here, because you want to write these in terms of the sum description, and then you've got a big expansion to do, right? Because this here is a sum. So yeah, that would be a bit involved to do properly. Okay, but we have a ring out of this structure. And so the next question is, what are the units? So units of this polynomial ring, well, it could only be just plus or minus 1. Okay, because the product of two polynomials will be another polynomial, and given that they've both f and g would have x's in them, then the result will have x's in them, and there's no way to get rid of those, right? Because we don't have any nice property like we had with the omega in the last example. So the units in this case are just plus or minus 1.